Okay, welcome again to you all. The first presentation is about understanding the terms isomers and congeners to describe chemical molecules, because isomers and congeners are mixtures of chemicals that are listed under the Rotterdam and Stockholm Convention, or are those who are considered by the Conference of the Parties. The next slide, please. Can you see the next slide?
Oh, yes, we can.
Yes.
Okay. Okay, the webinar is first the introduction, then the application of these terms to the Stockholm Convention, a presentation by me again, and then by Hala, the application of this information on isomers and congeners for the chemicals listed under the Rotterdam Convention. So, what are isomers? Isomers are compounds with the same molecular formula, which specifies the number of atoms of each element in the molecule, but can have different structural formula. For example, there are chemicals which have no isomers. For example, hexachlorobenzene, which is a benzene ring with 6 chlorine atoms at each carbon atom, has no isomers. It has the molecular formula C6Cl6. But there are chemicals that are very closely related and which are produced by production processes of chemicals, and these chemicals have the same molecular formula but different structural formula. And there are different types of isomers. One is the structural isomer, and then we will look at stereoisomer. These are molecules that have the same molecular formula and also the same sequence of atoms, but differ in the three-dimensional orientation of the atoms in space. Because we talk about organic molecules, and the carbon atom has the possibility to bind 4 other chemicals, and these 4 chemicals are in different positions in space. And if a chemical has 2 or more carbon atoms, then these attached atoms can have different orientations. And what is important, why do we look at isomers? They may have different properties from one to the other. So in the next slide, we just see constitutional isomers. There is first the in the left, the benzene ring with an OH hydroxyl group and a methyl group CH3. And these 2 groups are just attached to each other. OH is at the top carbon atom, and CH3 is just at the next carbon atom, attached to the next carbon atom. And this is the Greek word which calls ortho, which means neighbor or next or something like that. And so then we have of cresol, which has the molecular formula C7H8O5. We have the orthocresol form. Then the CH3 can move to the next carbon, and then it is in a position, it's distant from the hydroxyl OH group by 2 carbons, that's called meta. And then in the third chemical, where the CH3 is opposite to the OH, that is called the Hara position. Okay. Then there are stereoisomers, which have the same molecular formula, which have the same structural formula, but now the chemicals, the atoms bond to the carbon can be different arranged in space. For example, the chemical C4H6Br2, which means with 4 carbon atoms, 6 hydrogen atoms, and 2 bromine atoms, has 2 geometric forms, a cis and a trans isomer. And stereoisomers are molecules that are the same, but one molecule is the mirror image of the other molecule. So when you have your left hand, there's a mirror in between, and your right hand, then you can superimpose it by a mirror. But you cannot. The right hand is different from the left hand. You cannot. The right hand and the left hand cannot put it on top of each other, because the two thumbs are showing in different directions. And the same geometry is available for chemicals, and there you see the example of the molecule alpha HCH and alpha HCH plus and alpha HCH minus, and these chemicals are the same in the number of atoms and where the atoms are standing, but not in the three-dimensional shape of these atoms. And again, this is important because these two atoms can have different chemical and physical properties. Then there are those stereoisomers which are called diastereoisomers, which are not mirror images of each other, and the example here is hexachlorocyclohexane, which has the same molecular formula, C6H6Cl6. The structural formula is the same. As you can see, for all there is the ring, the hexacyclohexane ring, which is this ring in the middle, and then for each molecule there are 6 chlorine atoms attached to that. But the chlorine atoms are sometimes shown towards us, which is the dark arm that connects the chlorine with the ring, or if it's dotted, then it shows sort of away from us. So that means alpha hexachlorocyclohexane, the top one, the bottom one, and the left from the bottom one show behind, away from us, and the other 3 chlorines show towards us. And then beta, there is 1, 3, and 5 chlorine. The top one, the third, when we count clockwise, 1, 3, and 5 are away, the others show towards us, and gamma is where the top one and number 4, when you count clockwise, are behind, and the other 4 show towards us. So these are the same chemicals, and if you analyze for carbon, hydrogen, and chlorine, you will have the same results. They have the same structural formula, the same molecular formula, they have the same structural formula, but in space they are different. And again, they have different properties. That is why we are talking about it. Yes, there is a question. Yes, we see in slide 7, we see a 3-dimensional picture, which is sort of done by the dotted. That means it is behind your computer screen. You see it goes to the back, and where there is a dark arrow, full black arrow, then they show towards you. That's right. Okay, then we come to slide 9, and I'm not sure actually how I get the text of this slide here on the screen, but I have opened the presentation, and I just can read what you should see there if I would be capable to move in the text. So congeners are related chemicals. It is a substance synthesized by the same chemical reaction, and then a number of chemicals it it produces, and it involves the replacement of one element of a compound with another greater number, and it results in similar compounds with slightly different properties. And the example that we have is in slide 10, and there you can see it. It is polychlorinated biphenyls. Okay, you have two benzene rings which are connected in the middle. That is the basic starting structure. And now you do a process with chlorine, and then you, if you add chlorine under high temperature or whatever the process is, you get now different chemicals. You get, when there is one chlorine, which would be in one of the positions 2, 3, 4, 5, 6, and so on, or at the right benzene ring, 2', 3', and so on. With one chlorine, you can have 3 isomers. Then you will have these chemicals with 2 chlorine, which is D, and you have 12 isomers, and 3, 24, and so on. The whole number of these, the 209, are the 209 congeners, so which are a mixture of mono, D, tri, tetra, penta, hexa, hepta, octa, nona, deca homologues, which just have one chlorine atom in the molecule more, and each of these now with 3 chlorine atoms at these 2 benzene rings which are connected with the biphenyls, you have 24 isomers. And that is sort of the most complex mixture you can have, are PCBs. So it's a mixture of isomers and a mixture of molecules with different molecular formula, because you have first 1 Cl, then 2 Cls, then 3 Cls, and so on, which are chemicals with different molecular formula. So this was sort of the introductory text. The first is there are some chemicals which just have the same molecular formula, the same structural formula, and have no isomers, stereoisomers, or so on, because they are flat in one, they are not 3-dimensional and so on, like hexachlorobenzene. This is what when we assess POPs, like most. And yeah, that was the introductory part, and then I will now try to use the information in the first presentation to look at the chemicals listed under the Stockholm Convention. Thanks for your attention for the first presentation. Okay. Quebec, shall I continue with the next one?
Yes, please. You can continue for your next presentation.
Okay. Now I will discuss the congeners and isomers that are listed under the Stockholm Convention, and I will also say something sort of why we discuss congeners and isomers at all, why are they a problem or not, and so on. And you can see in Annex A, elimination, you find pesticide lindane, then industrial chemicals, hexabromobiphenyl, hexabromodiphenyl ether, and heptabromodiphenyl ether, which are components of commercial octabromodiphenyl ether. You have polychlorinated biphenyls, you have tetrabromodiphenyl ether, pentabromodiphenyl ether, which are components of commercial pentabromodiphenyl ether. You have alpha hexachlorocyclohexane, beta hexachlorocyclohexane, and actually, if we also look at the chemical listed in 2011, we also should have endosulfan, because endosulfan also is a mixture of isomers. Okay, and that was in Annex A, and then we have in Annex C, unintentional production. We have polychlorinated biphenyls, and we have polychlorinated dibenzodioxins and dibenzofuranes. Now we have to be very careful when we talk about unintentional, and that we come back to that. So we had the case of lindane. The issue is that lindane, which is the gamma hexachlorocyclohexane, which you see on the right side of the presentation, was proposed by Mexico. And only this chemical, the lindane, the gamma HCH, has the insecticidal properties, the intended properties. That's why you produce this. But in the industrial production process, where you produce in industry, try to produce lindane due to the type of production process, and we didn't know it better in the past. You also produce at the same time alpha HCH and beta HCH, which you see left from gamma HCH, which are isomers, stereoisomers. And there were large quantities, almost more than 80% of alpha and beta were produced when you wanted to produce lindane, because you get a mixture of alpha, beta, and gamma. Then you separate the lindane, the wanted pesticide, and you have a lot of unused, big pile of 80% of your whole production is stockpiled, is waste, is alpha HCH and beta HCH. But these alpha and beta isomers are also toxic, persistent, and bioaccumulating. So they are also a problem. So the outcome was that originally lindane was notified by Mexico, the substance on the right. And then at the same time, the POPs review committee realized when they were looking at lindane that alpha and beta were also produced in the past. Okay, and the POPs review committee knew that alpha and beta also had POPs-like properties. So the question was, could the POPs review committee assess alpha and beta also, although only lindane was notified? Because the POPs review committee knew that there were big piles of alpha and beta laying around in the environment. And if only lindane had been listed, then in the future, any lindane production would have been forbidden, and any waste of lindane would have to destroy it. But alpha and beta, these big piles, would have no special attentions because they were not assessed as POPs. So the conference of the parties said to the POPs review committee, you cannot assess alpha and beta only if someone notifies it also. And then Mexico also proposed alpha and beta for listing, and after evaluation, all three isomers were evaluated and recommended for listing and were listed. But you have to understand that the listing of lindane, of the gamma, means no more production of alpha, beta, and gamma because they come together during production, and any sort of no trade, no use, waste treatment, proper waste treatment according to the convention. And the listing of alpha and beta means that all the stockpiles, the waste that are around in the environment, are now POPs waste and have to be addressed under the Stockholm Convention. So then, the problem was that technically just what happens in reality, that three chemicals were produced, only one was useful, the rest was waste, and then, with all the information and then proposal for listing, all three were listed as a POPs. Now, we had the case of commercial pentabromodiphenyl ether, which is a mixture of pentabromodiphenyl ether, which means 5-bromine, of tetrabromodoiphenyl ether, hexa, 3, and hepta. They are all in this compound you can find in a commercial mixture of this compound. So and each penta are isomers, and this group from 3 to 7 are congeners. Okay, so we have a big mixture of congeners. Now the question was for the POPs review committee. Now we have this mixture. Now what are the POPs? Are all POPs the 3-bromyl, the tetra, the penta, the hexa, and the hepta? And what the POPs review did is it was looking at the data that were available to them, to the committee, and the data were where it could be proven with the data that were available. It was possible to prove that the pentabromodiphenyl ether and the tetrabromodiphenyl ether, especially those that you see on the picture, the 2, 2', 4, 4' tetrabromo, and the 2, 2', 4, 4', 5 pentabromodiphenyl ether. And the number without prime describes the position of the bromine, which is compared to this oxygen bridge in the middle of the 2 molecules, and then in the left molecule on the top. And one bromine is in position 2. Position 1 is where the oxygen is, and 1 is in position 4. You have 2 and 4, and then 1 is in the second molecule. And to distinguish it, because it looks the same, you say 2' and 4'. And for the penta, it is a 2, 4, 5 in the left, and then 2' and 4'. And these two specific congeners, which are in highest concentration, were identified as the POPs. Okay, as you can see here. The outcome for listing then was an interesting discussion, and was a discussion when you have the 2, 2', 4, 4', which is called BDE 47 for simplification reasons, and the penta, and we have looked at them before, the BDE 99 were recommended for listing. The question was, what was with the other tetrabromodiphenyl ether, with the, the 3, 5, 3', 5', and so on. So where the bromine are sitting in different positions, which are isomers, structural isomers of the tetrabromodiphenyl ether. Do they have the same effect or not? And then in a preventive approach, the POPs review committee said we list the reason for listing. We identified POPs properties for BDE 47, BDE 99, but we assume that all other congeners and isomers of tetra and penta in the commercial mixture are also POPs. So when you measure, you have to measure the whole quantity of all tetra and penta. And especially the BDE 47, BDE 99 are markers. When you do monitoring and enforcement, then you measure these special congeners. The situation for commercial octabromodiphenyl ether was similar. It was a mixture of penta, hexa, hepta, octa, nona, and decabromodiphenyl ether. Most was hepta and octa, 45% hectabromodiphenyl ether, 33% octa. And so the story was the same, and you had a mixture of congeners. You had to identify what were the POPs, and the outcome was that hexa and hepta are expected to be POPs, these congeners and all isomers of that. And especially the markers were BDE 153, BDE 154, BDE 175, and BDE 183. And BDE 153, you see it's the top molecule of the two molecules is BDE 153, and BDE 154 is just the one below. So the whole story was a commercial mixture was notified, which consisted of a number of congeners and each congener of a number of isomers. What was done is that for specific congeners, specific isomers were assessed as POPs. Then one would assume that the other isomers have also, of this congener, have also POPs properties, all the isomers that were present in the original commercial mixture. And now we come to something which is totally different from the question of isomers and congeners, but another listing that is very complex. So now the last two slides are about a chemical called PFOS, and it's not the question of isomers and congeners. That means mixtures of chemicals which are just typically produced through chemical reactions and which are not just one chemical, like hexachlorobenzene or so, where you just have one chemical. No, you have a mixture of chemicals, and then the question is how to assess their POPs properties, and then the question is how to list. And that I've shown now for lindane, commercial penta, commercial octa. But now we come to PFOS. Now PFOS, and you see the chemical perfluorooctane sulfonic acid, which is the molecular formula is C8, and which is C carbon atoms, and the carbon atoms never get in these formulas. It's just where the F's are hanging on, so you can see that there is always these are the carbon atoms. There are 8 of them. Then there are, you can count 17 fluorines, and then there is an SO3 group, sulfuric group, and acid is attached to the last carbon, and that is perfluorooctane sulfonic acid. Now, when Sweden proposed PFOS, this acid, they also included in their proposal 96 chemicals that had this element in their body, because you can make now, you can make the salts, for example, out of this acid, where you just replace the H, the hydrogen at the right of the formula, for example, by a sodium Na. So you have the sodium salt, or the lithium salt with Li and so on. You can also replace the H by a fluorine, and then you have PFOS F, and so on. And there are also polymers where this is part of. And the PFOS, these PFOS, it salts, PFOS F, and other PFOS-related chemicals where the H is replaced by ammonium or by a longer polymer, are widely used in industry, and they all degrade. When the chemical is degraded by organisms, by microorganisms in the environment, what remains is the PFOS. This is what you can see on the screen, and this doesn't degrade almost at all. And it's very similar when you are not a chemist and you know when people who die, they are buried, and then 50 years later, what you find, all the flesh is gone, but what you find is the bones, which is very difficult to degrade. And then 100 years later, you just find the skull. And the skull you can see as the PFOS, in the whole thing. Everything else degrades, but the PFOS stays. And the PFOS is the problem. Okay? The degradation product in the environment is a problem. It doesn't matter whether it comes out of a polymer or it's just the acid itself or its salts. There is no difference for the environment. It just means that the salt degrades, dissociates very easily, and PFOS F and so on and other chemicals need some degradation of the molecule till the PFOS itself remains, maybe 10, 20 years. But as the PFOS itself doesn't degrade in 20, 30 years at all, then it doesn't matter whether something adds up in 10 or 20 or 30 years, it adds up, adds up, adds up. That's why we have to look at the PFOS, its salts, PFOS F, and the PFOS-related chemicals. Now, what was listed when we discussed PFOS? Listed was the acids, its salts, and PFOS F, because these chemicals, it was known that they would very, very quickly degrade in the environment to PFAS. And so they were explicitly listed. And then all the PFAS-related chemicals were listed in a way, it was said that any chemical that was produced with PFAS-F as an intermediate, and all PFAS-related chemicals are produced using PFAS-F, the listed PFAS-F as an intermediate. And so you don't have listed the chemicals name by name, only the acid, its salt, and PFAS-F, but through the listing that everything that is a result of a reaction which PFAS-F in the reaction process as an intermediate, which is a PFAS-related chemical, is also listed, but not by name, but by the production process. And so it is very important to know these PFAS-related chemicals, what are their names? And their names are available. The OECD, the Organization of Economic Cooperation and Development, has produced from their member states, industries, a list of 160 chemicals that contain PFAS as a structural element. So this is sort of not the 92 from Sweden, it's a longer list. And so that would be a list which is also available in the NIP guidances that have been developed for the 9 or 10 new POPs. Yeah, that was all I wanted to say about listing and assessing and listing. I mean, assessing a POPs is difficult, but it is easier if you just look at one chemical like hexachlorobenzene with one structural formula, no isomers and so on. It gets a little bit more complicated when you produce a mixture like lindane and alpha and beta. You have to assess all three of them to identify them as a POPs. And then it gets more complex when you just use the complex mixture of congeners like in commercial penta or commercial octa. It's difficult. The POPs review committee first has to say what is in there, what has the POPs properties, where can we prove with the experimental data where the POPs properties are, and then what do we do with the other isomers? And there always is a preventive approach. All the tetra and penta or the hexa and hepta other isomers are assumed to be POPs also. And then at the end, the complex example of a whole group of chemicals. So when PFAS is listed as one chemical, it can be 100 chemicals that are, behind this listing. Thank you very much for your attention.
Thank you very much, Rainer, for your great presentations. Now, our second presenter, Hala Arasa, will proceed on the presentation.
Hello, everybody, and thank you, Rainer, for the comprehensive introduction on isomers and congeners, which makes my life much easier when I speak now. I would like to talk about the relevance of isomers and congeners in relation to the Rotterdam Convention. Now, as you can see in the slide in front of you, we have the following chemicals which are listed in Annex 3, the hexachlorocyclohexane, mixed isomers, except the gamma, which is the lindane. The lindane is separated or is listed separately. Then we have the polybrominated biphenyls, the polychlorinated biphenyls, and the polychlorinated terphenyls. Now, in the case of HCH and lindane, I will be very brief since it has been explained in more details in the Stockholm part. Now, if we look at the chemicals, the first chemical we have in front of us, which is the HCH, the hexachlorocyclohexane, mixed isomers, and lindane, I will take the three, the alpha, beta, and gamma. Now, the HCH is actually the parent component and is as was mentioned earlier, and there was a very explicit example was in the first presentation Rainer gave about the 6 chlorines replacing the 6 hydrogens and on the cyclohexane, and how they were organized in the space, so the stereoisomers. The gamma was said by Rainer, and we'll confirm it here, is actually the lindane, which is a pesticide used mainly for lysis. Other isomers are the alpha and the beta isomers. These are byproducts, as was mentioned also by Rainer. When the gamma isomer, the lindane, is actually manufactured, we do get byproducts. Those byproducts are the alpha and the beta. And the problem, since we deal with trade, there are great or large number of stockpile waste in many manufacturing countries, which could affect the environment. Now, for the polybrominated biphenyls, this is a similar case as the polychlorinated biphenyls, where the example was given by Rainer for the congeners. It has the same, similarly as polychlorinated biphenyls, it has 209 congeners in the same orders as the polychlorinated biphenyl. So the congeners actually, they differ in the numbers and the position of the bromine atoms on the 2 biphenyl rings, which are attached to each other through a bond. The problem is that this was used in the past as a flame retardant, especially in plastic products, appliances at home, textiles, foam, laptops, TVs, and etc. It is actually listed in Annex 3, and to us, and of the convention, and to us, we know that the global manufacturing has been seized or stopped then, which is a good news. We go back to the polychlorinated biphenyls. Again, this example was given by Rainer in details. I will say that there is a set of congeners which are 209 and is mainly used as coolant and insulating fluid, lubricant oil, sealant, and flame retardant. Now, in countries that are using I would say transformers, and they use this lubricant or coolant oil in it, we still have a problem as a stockpile. So when they are phasing out the transformer, but on the other hand, there is still stockpile of the liquid, or we could see stains of the liquid. So this falls under both conventions. The trade is still possible in consent of import, if the consent of import is given to certain countries under certain rules. Now, for the polychlorinated terphenyls, there is a set of congeners. Believe it or not, there are 8,000 congeners or 8,000 possibilities of replacing the chlorine atoms on these 3 phenyl rings. And it is similar to the PCB in chemical and physical properties. The production has been phased out, which means the use has been also phased out. And to date, we don't know, we have no known trade on this compound. For the next COP, by the end of next month, we have, as Rotterdam Convention, we have 4 chemicals to consider: the pentabromodiphenyl ethers and commercial mixtures, the octabromodiphenyl ethers, commercial mixtures, and these have congeners and isomers, and a compound that has no isomers nor congeners, also as in Stockholm, the PFOS. So we will have the PFOS, perfluorooctane sulfonic acid, perfluorooctane sulfonamides, and perfluorooctane sulfonides, and I will speak about them in brief detail. For the pentabromodiphenyl ethers and commercial mixtures, we do have, or we know actually, but by what was mentioned earlier by Rainer, that there are numbers of congeners or many congeners by replacing the bromine with by replacing the hydrogen with a bromine atom. The pentabromodiphenyl ethers are the ether is actually considered the main component by at least one party that submits the notification and the final regulatory action. Now, in the Rotterdam Convention, we should have two notifications from two different regions. It differs from where the in the Stockholm Convention, the POP-RC considers any chemical that is submitted by any country. But in the case of the Rotterdam Convention, the Chemical Review Committee or the CRC has to receive two notifications from two different regions. Now, the production has been stopped in Australia, Europe, Japan, Canada, and the United States. The production of it in other countries is still possible because they still use it as flame retardant in firefighting. Now, the octabromodiphenyl ether, the commercial mixtures, similar to the penta, but with the greater numbers of bromine atoms, which means bigger number or larger number of congeners. The octabromodiphenyl phenyl commercial mixture is still traded as flame retardant. The production has been stopped in non-historically producing countries, but the releases of the chemicals to the environment from the past production, article, service life, and disposal measures let us end the article service of life. So therefore, we are fighting to stop the trade on such chemical. For the PFOS, now for the PFOS, and in the case of the Rotterdam Convention, there was, when we received the notifications, we had different nomenclature used in separate notifications of the final regulatory action submitted by the countries from different regions. So we are actually trying to include PFOS, perfluorooctane sulfonic acid, perfluorooctane sulfonamides, and perfluorooctane sulfonides. These are number of compounds. The names are actually recommended by the CRC, the Chemical Review Committee for the Rotterdam Convention, and was offered after compromising the wide range of all PFOS-related compounds. The production continues mainly in China, so China is actually the main producing country, and many uses including water stain repellent, firefighting, foam material, plating materials, and as impregnating agents. This is the case of PFOS for the Rotterdam Convention. So in the next COP, we will be having 4 chemicals. 2 of them actually have the first 2, which are the penta and the octabromodiphenyl ethers, and the commercial mixtures do have congeners and isomers. And then we have the PFOS, which is the third one, with its other chemicals as non-congener. And this was a brief introduction